Uh, on touching a metallic doorknob, when you have rubbed your feet on the living room rug or a car handle after a long drive, you often get an electric shock, just like this. So, why is it so? So, some of you would say that it's because of some naughty particles like the electrons that love to jump around, moving from your fingers to the metallic doorknob. So let's try to understand a bit about these electrons and how they were discovered. Let's try to see the story of the cathode rays. Till some years back, we used to have televisions which used the cathode ray tubes, or we call them CRT televisions. So the first person who actually produced cathode rays using low pressure and high voltage was Sir William Crookes. And soon after him, Michael Faraday, Julius Plucker, these people also conducted experiments along with Irish physicist Stoney, who happened to call these cathode rays, he named them because of their properties, some of their properties, as an electron before they were characterized. This was in the year 1891, right? So let's try to understand what exactly happens in a cathode ray tube. So as you can see here, in a cathode ray tube, it's a glass tube which contains two electrodes. The cathode, which is connected to the negative terminal here, and the anode connected to the positive terminal. The air inside this tube is sucked out to a vacuum pump to create a very low pressure. And then you apply a very high voltage. You apply positive potential here and you apply a negative potential, which basically means a positive charge is here and there is a negative charge here. And as soon as you do this, invisible rays, they emanate from this side, that means the cathode, and they start striking on the glass around the anode. Since they're produced from the cathode, therefore these rays are called cathode rays. A greenish colored glow is created here, and that is what we call as the fluorescence. So till this time, people were not able to figure out exactly what these cathode rays are made up of and why do they have these properties, or why is this glow there. So Sir J.J. Thompson in their 1897 was the first person who actually said that these cathode rays were made up of negatively charged particles. That means he was the first person to say that there could be something smaller than an atom. And therefore he is credited with the discovery and the identification of the electron, the first subatomic particle. So what exactly did he do? He basically designed an experiment in which he proved that these were particles, and he found out the force that it took to deflect them from their path. It's just like the amount of force that you need to apply maybe to move a car turn. So this is called the Thompson's experiment. It's very simple. In a normal cathode ray tube, if you apply a high potential difference and you produce normal cathode rays, then they would just go straight, just like this. But if you were to apply an electric field, like with the positive part of the field here and the negative charge here, and then created cathode rays, then these cathode rays, instead of going straight, would get deflected towards them. And the same thing was observed for a magnetic field also. That means if you put magnets instead of creating charges here, and light is not deflected, whether it's an electric field or a magnetic field. So by exactly measuring the amount of force required to deflect these cathode rays from their path, Thompson was able to discover the E by M ratio, or what we call as the charge by mass ratio of an electron. Now this is something which we will see later on in another video. So coming back to what are the properties of cathode rays. They travel in straight lines. So if you place a metallic object here in their path, then they're going to produce a shadow. Yeah. Similarly, we just now saw that the cathode rays, they get deflected in an electric field or in a magnetic field from their path. So that's another property of theirs. They get deflected by electric and magnetic field. Next, they move with a very high velocity. They have a high momentum. They have high kinetic energy. and therefore if you put a light paddle wheel here in their path, then this paddle wheel starts to rotate. This basically is a proof that these cathode rays have high momentum and high kinetic energy. And also, lastly but not least, these cathode rays, when they impinge on a heavy metal target, X-rays are produced. Okay. Furthermore properties, the nature of the cathode rays, that means these electrons, is independent of the nature of the cathode that produces them or the gas in the discharge tube. They affect the photographic plate, they can ionize any gas through which they pass through, they can penetrate through thin metallic sheets, and they travel with a very high speed nearly equal to that of light. A question that very often students ask, why do you need to have such low pressure and high potential in a discharge tube? So let's try to examine the situation. Suppose if you had very high pressure, that means the number of gas molecules would be very high, and the electrons or the cathode rays which are produced would start colliding with these gas molecules, and they would not be able to move so easily, and that in turn would create something called a space charge, or what we call as a normal traffic jam. Whereas in case of a low pressure, that means a situation pretty close to that of vacuum, the number of gas molecules would be less. That means there would be lesser collisions, and that would therefore allow the electrons to move freely. Okay. If the potential is low now, so you can imagine a situation that if a cathode is producing electrons, that means a positive charge is getting created on the cathode, and therefore an electron would get easily sucked back into it if the electron is not moving very fast, right? That means if you put a high potential difference, that means you put a very high positive charge on the anode, then the electron which is escaping out can easily overcome the attractive force from the cathode and move with a very high velocity towards the anode. Okay, so that's why we have low pressure and a very high potential. Coming to the last part is something interesting called the Thompson and Thompson. Not exactly the comics of Tintin, but rivalry between Germany and England. During the time of the discovery of electrons, the Germans thought the cathode rays were waves, okay, just like light. Whereas, the English, they thought that the cathode rays were particles, and both were proven correct, and done by J.J. Thomson and his son E.P. Thompson. J.J. Thomson proved that the electrons were particles, for which he won the Nobel Prize in the year 1906, and his son around 40 years later proved that these electrons were waves, and for which he also won the Nobel Prize. Like father, like son. So that's how we come to the end of our first lecture. Hope you had a good time. Till next time, thank you.